This is the Physics Chapter 6 final exam review video, and you're going to want to get out your final exam review questions. Yours will all be on one page. I've gone ahead and made mine a little bigger so that you could see them. So question number 1 says, what is the tension in the two strings holding up the sign as shown on, of course it says the board, and I guess this is the board, right? So we have a sign that has a mass of 8 kilograms. It may be hard for you to read, but 8 kilograms. T1 and T2, 70 degrees, 45 degrees. It's strung up that way. Go ahead and pause your video so you can draw that out, and then we'll figure out what T1 and T2 is. Okay, so we're going to want to get the sum of all the tensions in the x direction. We know it's equal to 0 because the sign isn't falling. All right, so it's going to be x direction is cosine, right? So we would have T1 times the cosine of 70 degrees plus T2 times the cosine, not 45, but it'd be, we're going from the positive x-axis, which is 0 degrees, so that would be all the way around to here. So that would be 135. And then we need to get the weight of this sign. That's going to be 8 times 9.8. All right, so the weight of the sign is 78.4 newtons. So the weight of that sign is going straight down. All right, so plus 78.4 cosine. What's the angle straight down? It's 270. And that's 0. And the cosine of 270, you can put it in your calculator, but it is 0. Cosine of 70, go ahead and put that in your calculator. It'd be 0.342. Cosine of 135 would be 0.707, but it'd be negative 0.707. So minus 0.707 T2 is equal to 0. So I'd have 0.342 T1 is equal to 0.707 T2. All right, so let's solve for T1. T1 is going to be 0.707 over 0.342 T2. So T1, put that in your calculator, is 2.07 times T2. That's as far as we can go, but we're going to use that and substitute in a little bit. So the sum of all the tensions in the y direction also has to be 0, or this thing's going to be falling or floating or something. So you go through this same process and just change out cosine for sine since it's in the y direction. We have T1 sine 70 plus T2 sine 135 plus 78.4 sine 270 is equal to 0. Sine of 70 is 0.94. Sine of 135 would be plus 0.707. Sine of 270 is negative 1. So that'd be minus 78.4. So we'd have, now I'm going to substitute in that 2.07 T2 right there. So I have 0.94 times 2.07 T2 plus 0.707 T2, and let's move that 78.4 to the right. All right, multiplying those out and adding that up, you'll have 2.65 T2 is equal to 78.4. Solving for T2, you get 29.55 newtons. So that's one of your answers. How can you get the other one? Well, just plug back into 2.07 times T2. So T1 is going to be 2.07 times 29.55. And that is 61.18. Boom. All right, pause if you need to, and we will move to number 2. All right, number 2 may take me longer to draw the picture than it does to work the problem, but normally I would, of course, draw this on the board in the classroom, but this is our balance system. So we have a fulcrum, and we have a series of weights hanging down. So the first one is 2 kilograms. All right, so sorry if that's hard to read. 2 kilograms is what that is. The second one is 3 kilograms. Make it a little bigger so maybe I can. All right, and then we've got one over here we're trying to figure out. So I'll just put a question mark. What is the mass of that one? And then I've got one that is on the end down here that is 1.5 kilograms. We need to know the distance to the fulcrum, so this distance is 0.8. Okay, that's in meters. I'm not going to put the M in there. The distance from the end is 2 meters. All right, and then I've got from here to here is 1 meter. And 1.5 meters between those two. Now, we got to be careful. It's the distance from the fulcrum to the weight. Okay, so it asks us to find the mass, all right, what mass is placed 1 meter away. Okay, so we want to know the mass. If you want to know the weight, then you'd have to convert it to the weight afterwards. We're given everything in masses. So we just set the left side equal to the right side of the torques generated. So we would have 2 kilograms times the distance, 2 meters, plus 3 kilograms. That distance is 0.8 meters. And that's equal to X kilograms, we don't know what it is, trying to figure it out, times 1 meter plus, now be careful, it's not 1.5, it's the distance between here and the fulcrum. That would be 2.5 meters. So 1.5 kilograms times 2.5 meters. All right, so here we would have 4 plus 2.4 is equal to X, 1 times that X, 1.5 times 2.5 would be 3.75. Kind of dispense with the units. So X is equal to 2.65 kilograms. All right. So I think it did. It took me longer to draw it. So if you have one like this on the test, you'll have an illustration sheet. All right. You won't have to go through that. All right, 2 down, 2 to go. Number 3. So that one we just did was the easy one. Pretty much all of chapter 6 is hard except for those fulcrum problems. So this one says, number 3, what's the acceleration of a 100 Newton bunghole down a ramp that makes a 43-degree angle with the ground? Okay, well, let's draw it out. So this is 43 degrees. It's got a barrel. All right. And the barrel, we know it weighs 100 newtons. So this would be W sine 43 degrees. W sine theta is the gravitational force pulling it down. We know that we have friction going back this way. And then the normal force is the weight times cosine theta, or weight times cosine 43 degrees. Okay, so we know the weight is 100 newtons. All right, so that force down the hill, let's call that big F. It's going to be 100 sine 43 degrees. All right, and that is 68.2 newtons. So we'll use that in a minute. The normal force, we need that to get the friction. Normal force is going to be 100 cosine 43 degrees. You just got to memorize that. Down the hill is sine, normal force is cosine. And that is 73.14 newtons. We know that friction is equal to mu sub k times the normal force. So that's 73.14 times, and mu sub k is 0.12, so a very slick ramp. So our frictional force is 8.78 newtons. So not very much because it's such a slick ramp. All right, so we know that the sum of the forces is equal to mass times acceleration. I am going to have to get mass. Let's go ahead, calculate that. It's going to be 100 newtons divided by 9.8. All right, so just a little over 10, 10.2 kilograms. So I'll have to plug that in up here. So we've got the force down the hill, F minus the friction is equal to mass times acceleration. Down the hill, 68.2 newtons. Friction is impeding the barrel's progress at 8.78 newtons. Mass is 10.2 kilograms. And we are solving for A. All right, so A is going to be 68.2 minus 8.78 be 59.42 over 10.2, which is 5.83 meters per second squared. Okay, so definitely an important problem. I consider these kinds of problems as absolutely paramount, so that should give you an idea of whether it will be on the final or not. All right, pause if you need to, and we'll finish this up with a pretty long problem. All right, in number 4, we've got a situation, we've got some barrels. And those barrels are being pulled with a force of 2,500 newtons. We want to know what's the acceleration of the barrels and the tension of the rope. All right, so we're going to have to draw this out, kind of label everything. so we've got a 100 kilogram barrel. So normally I would have drawn this on the board. An 80 kilogram barrel. They're attached with a rope. We want to know the tension in that rope and the acceleration of the whole system. We know that, let's call this barrel, we'll call this barrel 2. And we'll call this barrel 1. And we know it's being pulled with a force of 2,500 newtons. We do have friction acting against this. We'll call that F sub 2. We have this friction. Call that F sub 1. So let's look at barrel 2 first. Okay. What are the forces? Well, you would have the tension pulling to the right minus friction pulling to the left, and that's equal to the mass times the acceleration. Well, let's get the friction. F sub 2 is equal to mu times the normal force. The normal force is just equal to the weight. So the weight is 100 times 9.8, right? 100 kilograms, 9.8. So that would be mu sub k. All right, and our problem is 0.15. Normal force would be 980. All right, so the friction in barrel 2 is 147 newtons. So I'm going to plug that in right here. I'd have T minus 147 is equal to 100 kilograms. I'm going to get rid of the units right now, but that's the mass, 100 kilograms times A. So tension is equal to 147 plus 100A. I can't do anything else with that, but I'm going to use that in a minute. Now let's look at barrel number 1. Okay, it's the same kind of thing. I've got 2,500 to the right minus the tension to the left, right? The tension on this barrel is pulling against it, minus the friction is equal to mass times acceleration. Okay, we can get friction. That's mu times the normal force. The normal force is just the weight, so that's 80 times 9.8. All right, that'd be 784 newtons. All right, so 0.15 times 784. So the friction of barrel 1 is 117.6 newtons. All right, so now I can plug this in. 2,500 minus what's we don't know T. We know it's 147 plus 100. I could actually plug that in now, but I'm not going to. Minus 117.6 is equal to the mass 80 kilograms times A. All right, 2,500 minus 117.6 is 2382.4. Right, so 2382.4 minus T is equal to 80A. So rearranging for T, it's going to be 2382.4 minus 80A. That's just the algebra. Take your time. Move the T over there, move the 80 to the left. Now I have an equation for T and another equation for T. We can set those equal to each other. So I would have 147 plus 100A is equal to 2382.4 minus 80A. All right, let's move that 80 to the left. I got 180A is equal to 2382.4 minus 147, that's 2235.4. So A would be 2235.4 divided by 180, that's 12.42 meters per second squared. Boom. Now it also asks for the tension. Oh my goodness, don't forget to do that if it asks for both. You got to plug back in. I'm plugging back in right here. 147, that's the easier one, right? Plus 100 times 12.42. All right, we'll just plug it in right there. All right, and that's 1,389 newtons. I've had students do this before, do all this work and then forget to finish it out and get the tension. Man, I don't want you to do all that work and not get the full credit if you did it right. All right, that is it for the Chapter 6 final review. The rest of them are going to be shorter than this. This is definitely the longest video in the bunch, but I believe, listen to me close here, this will give you a clue. I believe this is the most important chapter. I actually believe this is the most important chapter. The most important chapters in this book are 2, 4, and 6. So one of those most important chapters is going to be on the final. So what do you think? You think it's going to be represented or not? We'll see.